Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, so today session we're going to extend further regarding electrostatic issue. As mentioned in our weekly schedule of our course information, week number 3, by now we should extend the discussion regarding electrostatic involving other parameters. Not only electrostatic field intensity, we're going to talk about other parameters associated with electrostatic world. So let's recap what we have learned until now. We have been informed the source for electrostatic field going to be stationary charge. With that, I'm going to present my general representation of a stationary charge with a symbol rho v. And we know that rho v is a symbol for volume charge density. And why we choose this to be our general representation for our source? Because we can assume point charge can reside inside a volume charge. Similarly, line charge also can be in a volume charge, and surface can also have that same characteristic. So by taking rho v, we are representing that to be our general representation for a stationary source. And we have seen this particular source going to emit what is known as E, and E is symbol known as electric field intensity. So that should be what we have learned so far. How be able to determine E from the source? This can be determined by a law which is known as Coulomb's law. Okay, so that's what we have learned until now. So then we can say to ourselves, actually, E is not only the parameter that is emitted by a stationary source. Stationary source also can generate other parameters such as, I'm going to use symbol now. This is known as electric flux. Okay, and another parameter that also generated by stationary charges is known as symbol D, and D is known as electric flux density. So what we're going to continue after this, we're going to talk about these two issues. Okay, first we're going to talk about this known as electric flux, and this is known as electric flux density, and this information can be obtained from our textbook if you open to section 4.5. Okay, so it mentioned about this issue. So I'm not going to repeat what mentioned by Sadiku. Here I'm going to summarize what this issue all about in a easier approach, so that we can complement what I'm talking about now with your own reading later on from our textbook, so make you understand the issue much more clearer. So I'm going to talk about the first parameter emitted by our source after electrostatic field intensity, known as electric flux. So electric flux is the one that we're going to talk now. Okay, so and then the symbol to represent our electric flux is going to be this symbol. So you might see the same symbol going to be used later on when we in the world of magnetostatic field. So that's going to be discussed in other situations. But now we are focusing on electric flux with this symbol. So from Faraday, okay, Faraday postulated this issue. What is electric flux? So for him, electric flux is just lines. So Faraday said that number of lines coming out from a source, that should be electric flux. And this line is a scalar, meaning that there's no directions. Okay, let's understand further in this analogy. Let's say you have 3 different point charge. So the first point charge let's say I'm saying to be black in color. Let's say the value here is 3 coulombs. Okay, and then the second point charge, for sake of comparison, let's make it to be 5 coulombs. And the third point charge, let's say 10 coulombs. So 10 coulomb for the red point charge, 5 coulombs for the blue point charge, and 3 coulomb from the black point charge. And Faraday stated that lines coming out from this particular point charge having same value as the magnitude of the point charge. What does it mean? If we are having 3 coulomb point charge, therefore there's going to be 3 lines coming out from the source. So this line is presumed to be our electric flux. So for 5 coulombs, we're going to produce how many lines then? That's good, 5 lines. Okay? And for the red point charge, from the magnitude, I'm going to draw 10 lines coming out from the source. Okay, so that should be the lines emitted by the source, and these lines are assumed to be known as electric flux. Why this is important? Let's say we do not know the values. Okay, we do not know the actual value of the magnitude charge value. So we do not know the magnitude of each charge. So we just see this as the graphical representation of our source. So when we ask ourselves from these 3 examples, which particular charge having the higher magnitude? And for sure, from this graphical presentation, we're going to confirm to ourselves that the point charge in red actually having the highest magnitude. Why? Because we can see more flux line emitted by the source. So that's what flux for, just to support, to validate, to strengthen the argument of researcher or scientists in this unseen world, because we cannot see the field. So we have to create a method to support our argument in a simpler way. So with that, the conclusion of Faraday, what he said, that the flux line, okay, that's what he's going to conclude now, is equal to the charge. Okay, that's what Faraday states. The flux, the line coming out from the source, is equal to the charge. So what is important here, we have to make sure when we compare charges, all these charges should have the same magnitude, meaning that if I'm using this in a Coulomb unit, all the other 2 should also be in a Coulomb unit. If I'm using one in microcoulomb, the other 2 should also be in microcoulomb unit. So that should be the argument regarding electric flux. As a conclusion, just a line emitted by the source, and the number of line is exactly the same as the magnitude of the charge of that particular source. Okay, so let's go on to the second parameter, which is the D. So the D, which is our symbol for electric flux density. Okay, we have been informed before, when you have a source, let's say a point charge, okay, this is our point charge, it's going to produce electric flux. Okay, I'm just draw part of it. So that should be what we assume to be at the moment, the level we are at the moment. We can know, we can say there's going to be a line emitted by the charge. So now we're going to change the characteristics slightly different. So instead of knowing the total number of flux line, we just want to, let's say, investigate at certain point in space. Let's say I want to analyze at this particular point regarding the electric flux. So since it's at a point, so I have to narrow them smaller. So I have to analyze at the smaller aspect. So in order to support my argument to that smaller aspect, I'm going to create a sample area because I'm going to put a limit. So therefore I'm going to create an area. So the area must be small. So small meaning that it must be having what is known as area given as ds. So from this simple diagram, we can see that there's a number of lines that passing through this area. So the whole number of lines, the total number of lines, we call it electric flux. Therefore, the number of lines passing through this shaded area, we're going to denote as d electric flux. Okay, so by using this observation, we can define electric flux density D is equal to, okay, the number of lines passing through that small area. We're going to call it the electric flux, and then we're going to divide it by the sample area that we are creating to capture the line. So that should be the definition of electric flux density. Okay, just flux line divided by the small area of your sample. And if you rearrange the mathematics, what we can say here that this d flux E can be denoted as d multiplied with ds. But you have to be careful now. What I mean by careful, because the arrangement of this area ds is very important. So meaning that if I slightly change the position of this area, the result of my flux capture going to be changed. Okay, even though the magnitude of the area is remain the same. So what's important here, we not only deal with the scalar, what is meant by scalar, the magnitude of the area, we also have to deal with the position of this sample area. So with that, we have to consider vector now. Okay, because that's important. Because as you experience using your handphone, by changing the arrangement of your handphone, you're going to see that the field strength detected by your handphone might be different compared to different arrangement, even though the area of your handphone remain the same. So therefore, that is a proof why the surface vector is very crucial in that particular application. Okay, so in that argument, similarly, as you can see logically here, even though the area remain the same, by changing the arrangement, the orientation of this small area, that's going to play a crucial role regarding our analysis. Therefore, as a conclusion, we have to work that particular behavior with the parameter known as surface vector. So when we look into this mathematics, it's not valid. Why? Because electric flux is scalar, as mentioned earlier. It's just a line emitted by our charge, no direction, but yet there's a surface vector here. So how to make this equation valid? Yes, so you have used to we have to use what is known as dot product. So therefore, we have to do this in order to verify the correctness of the mathematics. So with that conclusion, we can conclude now d is a vector, and electric flux density is a vector entity. It's not a scalar, even though electric flux is a scalar, but electric flux density is a vector. So as a conclusion, we can conclude the mathematics now. Electric flux E actually equal to, mathematics was known as electric flux density dot with the sample area in our analysis. So that should be our conclusion regarding electric flux density. So let's complete our initial diagram that we put forward earlier. So what we said here. So we said before that flux electric can be determined from the source using what is known as Faraday postulate. Then we might be able to link these two together using the equation we just developed just now. So let's fill all the information in this table properly. So we are saying electric flux equal to D dot with ds, and please make sure now D is a vector. Then we are saying that electric flux based on Faraday postulate equal to the charge. So that's what we have done so far in terms of expanding the discussion issue regarding electrostatic field with the inclusion of electric flux and also electric flux density in our discussion, because these are the other parameters that been generated by our stationary charges. Okay, so what I'm going to do now, I'm going to extend further the discussion by doing example focusing on electric flux density. So what we're going to do now, we're going to do example from handout number 5. I'm sure you can obtain this handout from your e-learning website if you download it. Okay, that should be our reference of discussion reading examples of what? Electric flux density. Okay, we're going to talk about electric flux density. So I'm going to solve now problem number 1. Okay, so let's read the question now. The question said, find the electric flux density, and it's supported by the symbol that we have seen before, vector D. Emanating from a point charge, so now the source of our D is a point charge of magnitude Q, and the unit here is Coulomb, at the origin at an imaginary concentric sphere of radius r. So that should be our problem. We need to find what is the D that been generated by a point charge Q. Okay, so what we have now, a point charge located at the center of our concentric sphere. So just to make it easier, we're going to attach coordinate now. And what I mean by that, I'm going to link this problem to a coordinate known as spherical coordinate system. Okay, that's the norm when we solve EMT problem. We always link the problem to the proper coordinate system. Okay, so that should be the center of our origin. So what been stated by the question, what exists is a imaginary sphere. Okay, so that should be our imaginary sphere stated there. And this sphere having radius r. And the value of this particular magnitude is Q Coulomb. So we've been asked to determine the D generated by the Q. So to answer that, I have to propose a position in my diagram, my D location. So what I mean by that, let's say I want to find the D located at this particular point. This D, if we draw carefully, actually appear to be on the surface of our imaginary sphere. So therefore, the radius of this location that I want to determine, the D, actually the same as the radius of the sphere that we are referring here. So what should be the D here? Okay, what should be the D that we're going to calculate on that particular X point? So the way we do it, we have to use the equation that we seen before, that we proved together, that electric flux actually equal to D dot ds. We're going to start with this particular equation. Okay, so what is this? This electric flux density, and this is the sample area. So this is going to be my starting point. I'm going to relate this equation to my diagram now. So I'm going to say now, electric flux is the total flux captured by this sphere. Okay, so total flux means that I have to introduce a completely closed surface, meaning that there's going to be no hole on the surface. All the flux going to be captured by this surface area. That's why I indicate this symbol, complete closed structure. So the ds should be the sample area that referring to this particular segment of the surface sphere. And then from our previous encounter, we know that this can be replaced with a variable known as which one now? You have to first refer to spherical coordinate system. So please refer to your handout number 2, the table under the column spherical coordinate system. Yes. Okay, then we know there are going to be 6 surfaces. Surface number 1, 2, and number 3. So which one should be the one we use to represent our ds in this particular situation? Good. Yes, this should be r square sine theta d theta d phi in r direction. That should be the one that we select for this particular substitution. So you have to see this logically. Okay, so therefore this is important. By choosing a wrong substitution, you're going to get wrong solution. And the way we're going to substitute based on what we observe. So from here we observe that this particular sample area does correspond to surface area number 3 of our box structure that we developed before. So that's done. Now I'm going to look into my D now. So I do not know the D in specific substitution. So since I do not know the specific substitution, I have to substitute with general representation. So I'm going to ask myself again, okay, I'm using which coordinate system for this particular application? So all of us agree, spherical. Therefore, I'm going to say to myself, I do not know the D to be in a specific way. I'm going to substitute with the general representation by saying the D, let's say, consists of R component as well as theta component and as well as the phi component. Because while I'm doing this, I do not know which of these 3 components going to be my final solution. I'm just giving a general guess. But why I'm using this particular equation, because we already agreed the coordinate that we are using for this problem is based on spherical. So spherical should be represented with R component, theta component, and phi component. Okay, let's continue. So the mathematics now, if you do the mathematics here, I'm going to use the the multiplication now. So dot product is what we refer now. So I can see now dr in R component dot with r square sine theta d theta in the r component. So I can see the r unit vector dot with the r unit vector with n with 1. Okay, so therefore I'm saying to myself, okay, so the first thing I'm going to see now, that is going to be dr r square sine theta d theta d phi, and there's no more r direction because the r unit vector here, when you dot product with the r unit vector, this particular term, the end solution is equal to 1. Okay, remember dot product also known as scalar product because the final solution of a dot product is a scalar. So therefore, you don't have any direction after the multiplication. So let's continue for the second term. Okay, the d theta in the theta direction dot with the term in r direction. So I can see now the theta direction dot with the r direction with n with 0. So therefore, I'm going to set plus 0 because the unit vector theta, when we dot with the unit vector r, the final solution is 0 due to the angle between these two unit vector is 90 degrees. Cos 90 degrees is equal to 0. Similarly, the phi dot with the r also with n with 0. Okay, so I'm going to do the integration now, double integration, because I can see two variables here. First, the theta should be from 0 to pi, and then the phi from 0 to 2 pi. So the final solution here is equal to dr 4 pi r squared. But let's ask ourselves now, the question asks for what? The question asks us to determine what is the electric flux density. So we have to find what should be our dr here. So electric flux density so we're going to put d now. So I put r first just to make it easy. So flux electric divided with 4 pi r squared. But when look into this problem, there's no flux electric information be given in the question. What been given in the question is the charge, this imaginary spherical surface, so nothing else. So therefore we cannot use the parameter not been given by the question to conclude our solution. So we have to change it slightly. So what we can see now, we already know based on Faraday proposal that the number of flux line is actually equal to what? Yes, Q. So with that argument, we are now changing that the flux line now will become Q divided with 4 pi r squared. Okay, so since electric flux density is a vector, so we have to change to a vector solution. Must be magnitude, as what been proven before, 4 pi r squared. And then when we look into the D is focusing on this substitution. The magnitude obtained already by this mathematics, then we have to add the direction, and the direction is r. So with that, that should be our solution. Okay, so that's how simple way to find the electric flux density. So now let's go back to our previous model. So using this argument again, so what we say, the charge, okay, let's now we change slightly into our example before. So let's change into Q. Okay, so I'm going to change into Q. Okay, just make it related to what we discussed just now, the Q, a point charge. And then when we solve point charge, we know the E, based on Coulomb's law, is equal to what? Anyone remember the E? Yes, Q divided with 4 pi epsilon naught r square r directions. Remember that? Now, based on our previous example, when you have the point charge, we're also able to obtain the D. Okay? And from our discussion just now, the D is equal to what? Let's rewrite it again. It's equal to Q divided with 4 pi r square r. So let's compare our E and the D. You can see there's a lot of similarities. What is the E? Electric field intensity. What's the D? Electric flux density. But when we compare these two together, we can see there's some sort of nice arrangement that we can relate this together. So we can say now the E can be related to the D by do this. What is it? That the D actually equal to epsilon naught multiplied with the E. Okay, if you do this mathematics, when the E you multiply with the epsilon naught, so epsilon naught will cancel with this epsilon naught, we end with the equation without the epsilon naught parameter. So with that, we can conclude now. The D can also be known as electric field density. Why? Because we can relate with the E, electric field intensity, using this equation. So as a conclusion, the D can have two different interpretations. If I'm relating the D with the flux electric, the D is known as electric flux density, whereby if I'm relating the D to the E, I will name my D now as electric field density. So please be careful. Okay, the D can be represented in two ways. If you are representing with the flux, we call it electric flux density. When you are relating it to the E, we call the D as electric field density. So there you are. So now that's what we are introducing now, new parameter, electric flux density or electric field density, depending on what application the D is representing in your problem. Okay, so I'm going to go to the next issue now. Okay, remember that before I purposely don't want to solve problem based on volume charge source using Coulomb's law, because I did mention there's alternative law that we can use to solve the same problem. So anyone remember the name of the laws? Good. So the law is known as Gauss Law. Okay, so Gauss Law going to be our next discussion now, Gauss Law. Okay, if you open to your textbook, Gauss Law actually can be referred to section 4.6. Okay, that's stated in our textbook Gauss Law. So let's talk about the overview about the situation we are now. As mentioned, a source for electrostatic field can produce two main fields. So the first field that we can relate it to be is the E. Okay, how we able to find the E from the source? We can use what is known as Coulomb's law. And from our experience solving problem using Coulomb's law, mathematically it might be a challenging thing. even though it's not that difficult to most of you, but some of you might find it to be a bit complicated due to the involvement of integration that sometimes might be complex. That's what we face based on our previous encounter, especially from handout number 4. Okay, and also we learned just now the stationary charge also can produce another field which is known as D. And the D here we call it to be electric field density. So for us to find the D, we can use a method here, okay, alternative method we can call it, and this alternative method is known as Gauss Law. Okay, so for us, Gauss Law is just an alternative approach of finding D, finding the field when we been given a charge distribution or stationary charge distribution. And these two terms of the field can be linked together using the standard equation you just saw just now. The D is equal to epsilon naught E, because we're still in the world of free space medium, or in a vacuum medium. That's why we use the denotation of epsilon naught. Okay, so now you can see if I want to find the E given by the question, I can use two approaches. I can use either Coulomb's law approach, or I can use a simpler method, which is Gauss law approach. Then from the Gauss law, I be able to determine the vector D, or electric field density. Then I need to convert from the electric field density to electric field intensity using this standard equation. So that's what we mean by alternative approach. Okay, you can use Coulomb's law or Gauss law. It depends on you. You decide which law that you want to adopt in your solution. Okay, as I mentioned, Gauss law is a simple method compared to Coulomb's law mathematically. So unfortunately, not all cases we can use Gauss law as the applied approach. Okay, not all cases, meaning that Gauss law can be used only in certain cases, whereby Coulomb's law can be used in all cases. So in any problem, you can adopt Coulomb's law as the method. But when you want to use Gauss law, you have to remember not all situations can be used. So we have to first now propose the condition where you can use Coulomb's law. So this condition solely comes from the information of the source. So you have to look at the source given by the question. From there, you have to justify whether Gauss law can be used or not. So which cases allow Gauss law can be used? Okay, the first case, when you have a source as a point charge. Okay, when you have a point charge, you can use Gauss law, you can use Coulomb's law, doesn't matter. It's not that difficult. The second condition that we can use Gauss law is when you have infinite line charge. You have to see the word now. What is it? Infinite. Remember infinite line charge that we talked about before? Yes, that should be the case that where you can use Gauss law. If you are dealing with finite line charge, you cannot use Gauss law. You must use Coulomb's law, as what we have done in our previous example. Okay, case number 3, infinite surface charge. Okay, we have done example as well regarding finite surface charge and infinite surface charge under the category Coulomb's law. But for Gauss law, only applicable when we have infinite surface charge. And finally, we can say here volume charge. Okay, so now this is why you can see I purposely don't want to solve volume charge problem before using Coulomb's law, since I know that the same problem can be solved using Gauss law, and Gauss law method is much simpler mathematically compared to the Coulomb's law. So I'm going to show you about this as a proof later. Okay, so that should be the first criteria that we must look into when we want to use Gauss law. What cases of the charge distribution that allow us to adopt Gauss law? So now, what is Gauss law? Okay, Gauss law. Okay, so let's assume you have this scenario. I have 3-point charge. One, I'm going to draw here. I'm going to call it to be Q1. Then I have another point charge located here. I'm going to call it to be Q2. And then logically you can see now I'm going to draw my third point charge here, Q3. Why I'm going to draw only 3-point charge? Because my pen only have 3 different colors. Yeah? There's a reason why I'm doing this. So okay, so that should be our source, point charge. Okay, 3-point charges. Now I want to determine what in my model, the D. So I want to find the D. Let's say I want to find my D here. That should be my, what should be the D here? Okay, using what method? Gauss law. So when I want to use Gauss law, this is a must. I must choose my imaginary area, and this imaginary area is acting as a sensor. So this area must pass through this point of interest. Okay, let's say this is my imaginary area. Okay, what's this? This is my reference, and this area must have 2 characteristics. What it should do, it must pass through the point where I want to measure the D. You can see now if I move the D position to be somewhere else, this area going to be shifted as well. So it's going to follow where the D location I want to determine. So it's like my probe. It's moving based on where is my interested location I want to determine. So that should be the first characteristic. The second characteristic, it should be completely closed. Should be no holes. So therefore this sensor, I'm going to call it to be Gaussian profile. Okay, remember, if I want to use Gauss law, I must know where the location I want to determine the field. Then I must build a sensor which is known as Gaussian profile. What does this Gaussian profile does? It must pass through the point where the D should be determined, and the second thing, it must be completely closed. When you have done that, you are in the correct track of using Gauss law. So the third step now, we have to relate the structure to the equation. So Gauss law equation, state 1. It states here, the D dot ds must be equal to the Q enclosed. That's what Gauss law states. Okay, that should be the third step. From this equation, you can see that 2 sides of the equation. The left-hand side, which is red in color, and this left-hand side red in color. Sorry about my orientation. This should be the right-hand side. The left-hand side, right-hand side. So I must relate the equation to the diagram that I already built, the sensor that we already built. What we call the sensor is Gaussian profile. So the left-hand side of this equation of Gauss law must be related to what you extract from the surface of your Gaussian profile. So, therefore, in order to make this mathematical term easy, we should choose the shape of our Gaussian profile to be something that manageable. What I mean by that, meaning that we can use it either to be a sphere, a box, or a cylinder. Other than that, with non-uniform shape, you should try to avoid them. Because why? The consequence will come into when we want to solve this part of the mathematics. If the structure is simple in geometrical representation, therefore the mathematics here is going to be manageable. If the structure is going to be non-uniform in any way, the mathematics here is going to be unforgiving. So therefore you have to decide. All come back to you. You, the person, want to solve the mathematics. You choose which one that you want it to be. But for me, I always make it simple. Okay, then we go to the second part of the equation, the Q enclosed. Here, enclosed. Enclosed means that what actually the charge that reside inside this profile. That's why enclosed. Whatever you see, the charge inside this Gaussian profile, you should consider in your calculation. The charge that reside outside this Gaussian profile, we should ignore them. Okay, that's why the enclosed meant the charge that residing inside the Gaussian. For this particular example, what should be our equation will be? So we can see, yeah, there's Q1 located inside the Gaussian, and there's also Q2. So we just need to add Q2. Okay, then we should ignore Q3. Why? Because it does not reside inside the Gaussian. It residing outside the Gaussian. Therefore, it should not be considered into our calculation because this only referred to the charge that is residing inside the Gaussian structure. Okay, that should be the general overview of Gauss Law method. First, you have to look into, is it appropriate to use Gauss Law? If yes, then you have to know the location where you want to find the D. Then you have to develop the Gaussian profile. What is Gaussian profile? Two things, passing through the location of D and also must be completely closed. And finally, you must solve the mathematics of Gauss Law based on your own diagram of Gaussian profile. Okay, the left hand side of the Gauss Law must be referred to the shape, the surface of the Gaussian profile. The charge enclosed must strictly refer to the charge that residing inside the Gaussian profile. So there you are. That's what Gauss Law all about. Inshallah, it's going to be much easier than Coulomb's law. So shall we give a try? I think logically I'm going to go example based on this particular situation, the volume charge that we purposely avoid to solve using Coulomb's law. Okay, can you please go back to your handout? Okay, handout number 5. Okay, I'm good. I'm sure now you can see I show you handout number 5, page number 1 under the category Gauss Law. Okay, there are 3 questions, so I'm going to focus to question number 3. Okay, we're going to focus on question number 3. Okay, the question said here, a spherical volume of radius A contains a uniform volume charge density rho v, and then determine the electric field density in all regions. Okay, that is the question now. Question number 3. So we have not solved this question in when we deal with Coulomb's law. So now it's something new to most of you about this problem. So is a sphere. Okay, then the radius of the sphere is given as A. Inside the sphere, there's a volume charge, and then it's represented by our standard representation, rho v. So the question simply asks us, find the electric field density. Okay, find D, electric field density in all regions. That is the questions. So meaning that when we interpret the question, you want us to find what's the D here, what's the D here, or anywhere in this particular diagram. So in all regions, what should be the D? Okay, so there you are. So you're given a source, you need to find the field. Okay, so based on our model, we can use two methods here to solve for the D. We can use Coulomb's law, or we can use Gauss law. But Coulomb's law ends with a complicated equation. Gauss law, we can use it. Why? Because we have this source do agree with the fourth criteria of the charge allowed using Gauss law. What is it? Volume charge. Okay, so there you go. So I want to use Gauss law now as my method. So I'm going to write, okay, Gauss law going to be my approach. Now, what should be the next issue now? Yes. What should be the coordinate we use in this particular problem? Okay, so what should be the coordinate we should use here? Good. We should use spherical coordinate. Why? Because the source is a spherical shape. So therefore, with that behavior, we should use the suitable coordinate system, which is spherical coordinate system. Now, I can see now they're going to be two distinct regions. What I mean by that, my D will be based on position. I can see the equation of my D going to be different within this structure when compared with the D that representing the outer position. Okay, so with that, I'm going to make it easy by saying, okay, first I'm going to assume this to be my region number 1. What's region number 1? Inside the sphere. And region number 2 going to be outside the sphere. So I'm segregated the area. Why? To make this problem become more manageable. So first I'm going to focus on region 1. Okay, region 1 should be my interest now. I'm going to ignore region number 2. Okay, so remember what we should do when we want to use Gauss law? Good, I'm going to indicate where is the position. So what I'm doing now, I'm proposing to myself, this is my point of interest located in region number 1, where I'm going to do my Gauss law analysis. Okay, so what need to be built in Gauss law? Good, Gaussian profile. So the shape of the Gaussian profile should relate tightly with the selected coordinate system that you choose before. So with that, I'm going to choose my Gaussian profile to be a sphere, where the center of my Gaussian profile is coinciding with the center of my sphere. And then, since this x is not fixed, this x can be moved provided it stay within region number 1. I'm going to show that behavior by substituting the value of the radius of my Gaussian to be general representation of R. Based on which coordinate system? spherical coordinate system. So I'm going to define now based on rules now. I'm saying now region number 1 is true when the R always remains smaller than A. So I'm saying now I can move this position anywhere within region number 1 provided it always obey these standard rules. What is it? R must always smaller than A. So meaning that can only be inside this region number 1. If I put X here, I draw my Gaussian to be passing through the point X. But yet, the R here is still smaller than A. Okay? So now let's continue. So again, I'm repeating here. I know the location of my D. I build the Gaussian profile. Remember, the Gaussian profile might have two characteristics. First must be passing through the point of X. Second must be good, completely close. Okay, now let's do the mathematics now. Completely close. D dot ds should be equal to Q enclosed. Okay. So let's do the mathematics on the left now. Okay, so I know that we have done this before when we talk about electric flux density due to a point charge example. Okay, the same mathematics that we are referring now. So what should be the solution here based on the one that we done earlier? Yes, should be dr 4 pi r squared. Remember, we did this before, where I choose what should be the D. D should be general. ds should be r squared sine theta d theta d phi r direction. Then you end that mathematics with this solution as shown before in previous example. Okay, I'm going to focus on the Q enclosed now. So this must be very, very important for you to see this argument now. Q enclosed means that the charge that located within the Gaussian profile. So that should be my charge of interest. Is there charge located here? The answer is yes, because this is a volume charge. Correct? But based on this equation, whenever you want to consider this mathematics is only true for the case the charge that residing inside the Gaussian. Therefore, the only charge that I should consider here must be the shaded area charge. The charge that residing outside here, even though does exist, I'm going to ignore. Okay, so let's focus now the mathematics. What type of charge that we are dealing here is a volume charge. What should be the mathematics? Rho v dv. Okay, so I'm going to make it so rho v constant. Based on our spherical coordinate, what should be dv? That's good. R square sine theta dr d theta d phi. Okay, how many integration that we need to do here? That's good. Triple integration because volume. Okay, let's choose the limit. Remember, everything we do this must relate to our diagram. What should be our limit of R? Okay, the R must refer to the shaded area from where to where that the charge that we're going to consider in this calculation. Good, from 0 up to R only. Okay, up to here only. Therefore, I'm going to use this upper limit for my R. And then for the theta standard 0 to pi, phi standard 0 to 2 pi. Okay, so my solution now is becoming rho v 4 over 3 pi r cube. Okay. Now we have two sides now. One dr 4 pi r square. On the other side, rho v 4 over 3 pi r cube. So therefore, for d1, I'm going to put vector now, d1. Why? Because it's only true for region number 1. Should be equal to, I can cancel the 4, I cancel the pi, I can cancel the R. So it should be rho V R over 3 in which direction? R direction. That should be our solutions. Okay? See how easy it is? You must always relate the mathematics to our diagrams. Okay, but this only true for region number 1. We have not completed yet for region number 2. So let's continue for region number 2. Okay, for region number 2, so you see I'm repeating now, region number 2. So if you do as many examples, you can see all these things actually repeating themselves. Yeah? So region number 2 should be my second concern now. So I'm going to draw, okay, region number 2, let's say make it to be here. Correct? So this is location for region number 2. Then I'm going to build my Gaussian. That's good. The Gaussian just the same thing we did before, passing through our D location and completely close. Okay, and then the radius must be given as R, so that now I'm saying the R for region number 2 always greater than A. So you can see the solution that we obtain for region number 1 is not applicable for case in region number 2. Similarly, the solution that we determine for region number 2 cannot be used when we are looking at region number 1. They are totally separated. So region number 1 only applicable for region number 1. Similarly, region number 2 is true for region number 2. Okay, so let's proceed now. Okay, so the mathematics now should be completely closed. D dot ds equal to Q enclosed. Okay, if you do the mathematics properly, now you're going to see its repetition, 4 pi r square, and then here should be rho v 4 over 3 pi a cube. Okay, you must see now a cube y, because the charge is only 2 from 0 to a. Beyond that, in this region, there's no charge. Okay, therefore, the limit of integration for rho v in region number 2 only for the r from 0 up to a only, even though our Gaussian extended to r. But in this region, there is no charge. Therefore, that case, that situation been interpreted in this solution. Okay, and then finally what you can see for D region number 2 vector should be equal to rho v a cube over 3 r square. In which direction? R directions. Because the 4 pi, you can cancel with the 4 pi, but I cannot cancel the r with the a. They are different values, because the r is the radius of the Gaussian, the a is the radius of the volume charge. So let's finalize our solution by plotting the field distribution. Okay, let's do that. I want to plot the field distribution. Okay, I want to plot, let's say, the D. I'm going to draw modular because I'm just focus on the magnitude, and then I'm going to change with the R. So what should be the shape of my field distribution in this problem? I know that there are boundary that defining two regions. So this is my boundary. What should be the value of my boundary? That's good, A. I'm going to call this to be my region number 1. This is my region number 2. Okay, for region number 1, I can see the mathematics is directly proportional to the R. As the R increase, the field going to increase as well. So it's linear. So I'm going to say, oh, the field shape going to be like this, a linear like that. Okay, only up to region number 1 here. So it's obeying this equation. Once it's going into region number 2, I must obey this term. I can see now as the field increase, the distance going to be here, going to be at the denominator of this mathematics. So the D going to be decreased as the R increase. So it's not linear. I'm going to see it's going to be decaying, maybe like this. Okay, that should be my field pattern of the field distribution due to the volume charge, referring to question number 3 of handout number 5. Okay, I'm going to talk about this example Gauss Law more in my tutorial lecture number 5. So with that, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.